Okay. So finish up the examples from 4.1. We'll do 4.2, get going on 4.3. Monday, finish up 4.3 and do 4.4. You'll get the review sheet. Wednesday, we finish up 4.4. On Wednesday will be the chapter 4 quiz. There will not be a quiz prep that will be posted. The quiz prep will be at 10 o'clock Wednesday morning. And then the quiz will be at the end of class that went on Wednesday. It will be the last quiz of the semester. Okay. Test will be after Thanksgiving. Probably Wednesday after Thanksgiving. We'll come back on that Monday and review. And the finals are the next week. Any questions? Okay. So finishing up 4.1. Make sure you know how to use your calculator. You're going to have quite a few decimal questions. So if you don't know how to punch in the values on your calculator, the calculator is always going to give you the correct answer for what you plug in. So if you don't punch in the values on the calculator correctly, it's going to give you the wrong answer to the, well, it's going to give you the right answer to what you plugged in, but probably the wrong answer to the question, unless you know how to punch stuff in. You can't just show up on the day of the test, first time you're taking up the calculator and trying to use it. You got to start now. If your method of homework is the night before, I'm going to try to work backwards from the back of the book, or maybe not working through, but just kind of fly by night, which is a great rush one, but hey, rush is going to come in and do your work for you. He's not showing up. Neil Peart can't, but Peart can't, but at 5 in the morning, it's going to be here. If you know the name, which I'm going to go by myself. They're from Canada, okay? The natural base, E, the natural function, E to the X, natural exponential function. So, number 34, f of x equals e to the negative x. And they want us to plug in negative 3/4 for x. This is what I was kind of harping on in chapter 1, because this is going all the way back to chapter 1. This is kind of a nice review before you take the final, because it combines everything. You need to just substitute, then you work it out, because maybe you can actually simplify something before you plug it in. F of negative 3/4. Write it out. This is e to this negative, and then x is a negative 3/4. Not try to write it up here, plug it in, and simplify in your head, and hopefully you get the right answer. What happens if I have a negative and a negative? You get a positive. So what I'm going to type in is e to the positive 3/4. That's what I'll type in. Fewer things to punch in if I simplify before I actually punch it in. Now, according to the rules of exponents, we're not going to use them, but according to the rules of exponents, e to the 3/4 is the 4th root of e to the 3rd power, or e to the 3/4 is equal to the 4th root of e, and then you raise it to the 3rd power. We can convert it into a radical notation. We're not going to here because we have a nice button on the calculator that goes e to the power of x. That's the natural base function. Okay? The natural base function, e to the x. Above that is 10 to the x. That's the common base. 10 is the common base, 10 to a power. Those are the only two where you have the bases already set for us. This will do 10 to whatever power you want to plug in. This will do E to whatever power you plug in, because remember, E is a irrational number. It doesn't have a last digit. Like right here is the pi. So when you want the exact value of pi, you press the pi button. Otherwise, anything you type in, 3.14, that is an approximation, not a very good one either. That's only 2 decimal places. When you press the pi button, you get the exact value of pi because you're using the number pi. Okay. When we press the E button, we're actually using the number E, not approximation for E. E is approximately 2.781828, 2.7182818. It keeps on going forever. Doesn't have a last digit, doesn't repeat a pattern. So you just use the E button. And it's right above this guy that you're going to learn about today, LN, which is the natural log button. Every time we teach you something in math, then we teach you how to undo it. Add, we teach you how to subtract. Multiply, here comes division. We do exponential functions, we have to figure out how to undo an exponential function. Logarithms undo exponential functions. So what undoes a base E is the natural logarithm, and what undoes base 10 is the common logarithm. So those two logarithm buttons are right there associated with the base. And it's going to boil down to your acceptance that this is a language and your ability to translate. If you will translate what we're going to do today every time, you're going to get it. Not like you're going to get in trouble, but you're going to actually understand. Because it's all about translating, changing it from this into the other form, it'll work out. Rewrite it, you can do it. If you fight it, well, if you don't practice that way, well, I'm telling you right now, if you just translate it, it'll work out. You got to start from right now all the way through the end of the semester. So right here, all we're doing is punching this in, E to that power. Now, when I type it in, I'm gonna type this in long. I don't pay attention to what I'm doing. So to activate the E, because it's in blue, I have to go second, and then I hit the E button. There's E to the what power? So E, and I go 3/4, 3/4. Now, if you notice, it opened up a parenthesis if I don't close it. Okay. First of all, you should always close parentheses. But what happens if I do close? E to the 3 divided by 4, and let's close it. Wow, this is a crappy calculator. It really shouldn't allow me to do the first one. It really shouldn't. Because what it should have done is it should have raised E to the 3rd and then divided the whole thing by 4. Okay. Luckily, it came out. I have another calculator where if you don't put the other parentheses, the closing one, it gives me an error message. That's why I get paranoid about the parentheses. Because I always get used to that error message. So I'm always cautious about not having parentheses when I need. That's all you do. Here's what's going to happen if you don't press the second button first. If I don't press second, this is what's going to pop up. Not E to the power, but natural log. And if you're not paying attention to what you're doing something completely different. You're taking the natural log of 3/4, not E to the 3/4. So you got to know what you're doing. Okay? So on 35, this is what we want. G of x is equal to 50 e to the 4x, and we want to plug in 0.02. So g of 0.02, write it out. So this is 50 times e to the 4 times 0.02. Simplify. I mean, you can enter it in as we're looking at it right here, but this is 50 times e to the, what's 4 times 0.02? This shouldn't be taking this long.
4.02.
Yeah, what's 4 times 2 pennies? 8 pennies, right? 4 times 2 cents is 8 cents? 0.08. And we just type in 50. And then you don't have to, but you can put times e second, e to the 0.08. And you don't even have to put the 0 point. You can just put 0.08. $54.16. And we're supposed to round to the nearest thousand. So what place value? Is it the first, second, third, fourth, fifth? What decimal is it? The third. So this is the tenths, the hundreds, here's the thousand. So we're going to round and keep it a 4. 54.164. That's all you're doing there. That's 33 to 36. Okay. We just didn't finish those two. Point two. Inverse functions. Inverse functions undo other functions. It's how we solve when we can't solve. And what we've had is problems where we come across a question that we don't have an answer for. We know these answers. What's 2 to the 0? 1. What's 2 to the first? 2 to the 4. 2 to the second. 2 to the third. 8. 2 to the 4. 16. Somewhere between 2, or let's go between 4 and 8. Somewhere between 4 and 8 is the number 6. Somewhere between 2 and 3, there should be something that I can raise 2 to and get the 6, because 6 is in between the 4 and the 8, so the answer has to be between the 2 and the 3. 2 to what power is the 6? See, that's what we don't have the answer for. There's no perfect number that's going to give us a 6, because 2 is not, or there's no perfect power of a 2 that gives us a 6. 6 is not a power of 2. If it was a power of 2, we would have an answer for it, but we don't. So how do we solve something like this? 2 to the x equals 6. Now, if it was 2 plus x equals 6, we would subtract 2. If it was 2 times x equals 6, we would divide by 2. If it was square root 2 equals 6, we would square both, no, square root x, my bad. Square root x equals 6, we would square both sides. If it was x squared equals 6, we would take the square root of both sides. We can undo squares, we can undo square roots, we can undo multiplication, we can undo subtraction, division. X over 2 equals 6, we would multiply by 2. The 2 to the x. The power is the x. How do we undo when x is the power? We don't have something yet. We don't know how to undo that. So there must be some other crazy function that nobody thought of until the 1500s with Johnny Aiken came around. He, that guy from Scotland, and says, let's call it a logarithm. And the logarithm is the inverse function for the exponential functions. That's all it is. It's an inverse function. That's the name, is a logarithm. It's an inverse function for the exponential function. Logarithms undo exponential functions, and exponential functions undo logarithms. That's all there is to it. It's named, don't be frightened of it. It's just called a logarithm. Why is it called such a, well, that's just what it is. We could have called it boot. We just boot it. That's fine. Okay. My granddaughter would love that. She wants to boot everything. Okay. Here's what we have. You guys are so entertained. Usually you don't quit your day job, but this is one. Exponential functions. F of x is equal to a to the x. They have restrictions. A has to be greater than 0. The base has to be positive. The base cannot equal 0, and it has to be greater than 0. The base cannot equal 1. Can't have 1 to the x. So there's some restrictions in play. X can be any real number. Let's just say that x is between negative infinity to infinity. X can be positive, it can be negative, it can be 0, it can be fractions, it can be decimals, it could be pi. We can go 2 to the pi power. Just punch it up on your calculator to get the, a better approximation, but still going to be an approximation. So if you want the exact value of 2 to the pi, you write it like this. But I can use pi as a power. The base can be anything as long as it's positive and as long as it's not a 1. Those are the restrictions for exponential functions. And then along comes the inverse of the exponential function, logarithm. I want to make sure I get my spelling right. I learned not to feel myself spelling anymore. Logarithm is the inverse function for an exponential. In other words, it undoes exponential. So I'm going to rewrite this just a little bit, and I'm going to use some notation to make it work a little bit better with our definition. This is the log form. The logarithmic form. Listen to how I pronounce this. Log base B. Can everybody see this B? Log base B. Of X is equal to what? Log base B. So the logarithm is base B. The logarithm is base B. It's not B to the X power. It's a subscript. They're telling us information about what kind of logarithm we're using. Inside the logarithm, we're taking the logarithm of an X. So we're plugging X into this kind of a logarithm. Like this would be log base 5 of a 12. It's not 5 to the 12. It's a logarithm that is base 5 of a number 12. That's all. So it defines what kind of logarithm you're taking. What does it mean? We'll get to that in a second. Log base B of X equals Y. Translating it is huge. Log base B of X equals Y. So that's a logarithm form. And then we're going to want to convert this. We're going to want to convert which means rewrite in both directions. Sometimes we're going to want to convert it to this one, and sometimes we're going to go this way into exponential form. It just depends upon the question. B to the Y equals X. On the right, we have an exponential function, some base B. Before it was an A to the X. And over there, I know it's an A to the Y, but it's all about how it converts. Remember back when we did inverse functions, you switched the X and Y? Well, to change what we have here into this, the X and Y are switched. That's just how it is. But it's all in the translation. Okay. Remember our little rules. The base. When you have an exponential form, the base had to be positive and it can't equal a 1. The base of the exponent over here, same as this base over here. So the base of the logarithm has to be greater than 0 and it still cannot equal a 1. Okay.
Mr. Right.
Thank you. So the base is still, this base is the same as that base. Okay. We can raise it to whatever you want to raise it to, no matter what. You can plug in anything you want here. which means the answer over here can be any possible real number that we can get there. The exponent can be anything and everything.
Slippery.
Okay. So this y, since it can be anything when you have exponential form, the answer can be anything. It's, positive, negatives, radicals, fractions, whatever. Okay. No matter what I raise this to, I'll never get a negative number. I'll never get zero. No matter what I raise anything to, whatever power, if I raise something to a negative exponent, it's still going to be positive. If I raise 5 to a negative 3, it's positive 1 over 5 to the positive 3. It's 1 over 25. There is no way to change. Since the base is positive, there is no way to get a negative number out of this exponent. Since the base has to always be positive, there's no way when I raise it to a power that I'll ever get a negative number as an answer. Also, there's no way to get 0 as an answer. So this answer x would always be bigger than 0. Which means in here, this x, and because it's in blue, I should have used blue. This x has to be bigger than 0. In a logarithm, you cannot plug in negative numbers and you can't take the log of the 0. And it's wrong. Maybe I might just give it to you. I don't know. Doesn't like a listen to today at all. Monday it cut out on us, and today it's. How's that? So here's the restrictions. Base greater than 0 has to be positive, can't have a 1. Inside has to be positive, you just can't have a negative or a 0. The answer, anything we want. Same thing over here. Base has to be positive, can't be a 1. Power can be anything you want. The answer would be greater than 0 anyway. Okay. Log base b of x equals 1. Here's how you convert it. Anybody do yoga? I don't do yoga. Anybody do yoga? Does anybody see people do yoga? Maybe not yoga, but like meditation. And they kind of like get in that zone where they're doing that kind of chant thing, a little mantra maybe. Maybe in a TV show or something. Just nod your head and pretend you not understand what I'm talking about. This is your mantra. This is how you convert. Base b. Logarithm base b of x equals what? Base b to the across y. Base b, log base b of x equals what? Base b to the across the equal sign. B to the y, base to the across, base b to the across y, b to the y, equals what's inside what's inside the logarithm, and what's inside that logarithm is the x. Base to the across equals what's inside. Base to the across equals what's inside. Base to the across equals what's inside. Why am I the only one saying? Base to the across equals what's inside. Base to the across equals what's inside. Why am I the only one saying base to the across equals what's inside? And people are saying, well, am I ever going to pass this class? What do we need to do? Well, maybe you need to chant. I don't know. Base to the across equals what's inside. That's how you convert this into that. Base to the across equals what's inside. Base to the across equals what's inside. Because you're going to take this and you need to write it like this. Or you need to take this and you need to write it like that. It could be like this, or it could be like that. It could be like this. That would be a limited choice. That was slim. I'm coming up with that's the 90s. That's as close up as it gets to your age. That was slim. Really? You know who Crystal Walken is? He's in his 90s. Wow. Have you seen Pulp Fiction? Yeah, he's an actor. Don't make me tell you about this. But it's all you're going to do. Base to the across equals what's inside. That's going to convert logarithms into exponential. It will also convert exponential, not in a direct manner, but it'll convert exponential back into the logarithm. It's just filling in the blank, and then you work it out from there. Base to the across equals what's inside. That's how you take it apart and put it back together. And it's just that phrase. That's how you take it apart, and that's how you put it back. So a minute. Start with the nth logarithm in a minute. That's all there is. Okay. So let me do. Three, 4, 6. Okay. And come back to 2, 4, and 6. I would want to go straight to number 12. And this is what happens when you're not paying attention. Is I show you how to do this one, and it's like, I don't know how to do that one. Well, this is all you do. I mean, that's all we do? Yeah, that's what I said in class. Oh. I was like, okay, oh. Directions. Write the logarithmic equation in exponential form. And then it even tells you what to do. So number 12. You're supposed to convert log base 16 of 8 equals 3/4. And you're supposed to convert that into exponential form. There's nothing to solve, as you can see on the left-hand side and the right-hand side. There's no x to solve for. The left-hand side and the right-hand side, they're as simple as they're going to get. There's nothing to clean up. You're just supposed to show that you can translate logarithm form into exponential form. And the way you do it is to the across equals what's inside. What's the base of the logarithm? What's across? So base to the across, 16 to the 3/4 equals what's inside? 8. That's it. That's all I want from you. That's what you'll have on a test question. Convert it into into its exponential form. You don't do anything beyond that. Just convert it. In other words, do you understand how these two are related to each other? Because we can't go past this point unless you can do that step first. Now, little sticky point. This is 16 to the 3/4. This is not 16 to the 3/4. That's 16 and 3/4. You may have met 16 and 3/4, but I'm grading it looking that's 16 and 3/4. Or maybe it's 16 times 3/4. If I couldn't tell. So your handwriting is it's gonna screw you up because you might even think it's 16 and 3/4 instead of 16 to the 3/4. An exponent has to be a superscript. Top right-hand corner, smaller than the actual number. If I see this on a test, I might give you the benefit of the doubt and I say, circle and I go, too big. And like Goldilocks. And that power was too big. So it's not a power. I'll take off a point. So make sure your handwriting is cleaned up, especially now because we have superscript, we have subscript. It's at the base of the G. It's below or the foot of the G. Subscript below. Subway. Subterranean. Okay. Then 12. Right, so we'll come back to 6. And then 18. 18, they want you to write it as a logarithm. So 18, now this is a little tricky. Going from exponential into logarithm. 9 to the 3/2 equals 27. So I have a mantra to go from logarithm into exponential. Base to the across equals what's inside. But I thought about, okay, do I come up with something that will take exponential, change it back to a logarithm? Then it becomes, all right, now they got to remember two things. And I'm not putting it past that you can. So if you want to come up with one, go. But I would rather have you make sure you know one, and then let's work it back. We want to go backwards and remember that it's this. This came from log base something of something equal something over here. 3 boxes. And over exponential form, 3 things. And what we had from the logarithm form is we went the base of the logarithm to the power across the equals, base to the across equals what's inside. Here's where you start. The base of the exponent and the base of the logarithm are always the same thing. So the base of the exponent is 9, so the base of the logarithm is 9. That's where that's where you should start. Now, when you look at this right here, this is base to the across. The 3/2 came from the across, 9 to the across. Base, so where the 3/2 should go would be over here, 3/2. So that's where 3/2 goes. 9 to the 3/2 equals the 27 came from what's inside. So you just kind of write, you don't have to put the boxes, I won't mind if you do, but I would set up this, and you know you're looking to fill in these blanks when you convert from exponential back into logarithm form. Because we go from logarithm back into exponential, base to the across, now we just got to fill in the blanks go the other way. But it's predicated on base to the across equals what's inside. I don't know how many times I already said that today. It's got to be at least twice. No. So without using a calculator, we're supposed to evaluate f of x. So 24 f of x is equal to log base 16 of x. And then we're supposed to plug in 1/4. So f of 1/4, we want to know what is log base 16 of 1/4. Without calculator. Now, that's kind of important because your calculator doesn't even have a log base 16 button. So you wouldn't be able to punch this in anyway. Now, how you do it? Basically, the across equals what's inside. But wait a second, I don't have an across. Now you do. Log base 16 of 1/4 equals, I don't know. So we call it something. Log base 16 of 1/4, let's call it x. Because if I'm going to convert it into exponential form, I have to have something on the other side. So now I can actually convert this. Base to the across 16 to the x power equals 1/4. The only way to solve this is to get both sides written. And this is another new type of territory. Solving exponential equations. That means when the variable is your exponent, you need to rewrite both sides with a common base. So a very straightforward, simple example. If you had 2 to the x equal 8, then you want to rewrite both sides with a common base. 8 is a power of 2. So this would be 2 to the x, and over here, 8 is 2 to the third. And once you have a common base, they're both 2's, then this x has to equal that 3. Once the bases are the same, the powers have to be equal. So if I had 5 to the x plus 2 equal to 125, well, 5, you can't change 5 into anything else. 5 is a 5. But 125 is 5 to the third. So this 5 to the x plus 2, this is 5 to the third power. So once you have the same base, this x plus 2 is equal to that 3. So once you have the same base, you let the exponents equal each other, solve with the variable. X would have to equal 1. Okay? So over here, we have a 16 on the left, a 1/4 on the right. Now, 16 and a 1/4 are both powers of what? They're both powers of 4. 16 is 4 squared. So this is 4 squared to the x. And 1/4, remember, is 4 to the negative 1. If it's in the denominator, it has to flip up to match with the other one. 1/4 doesn't count. They have to both be in the numerator if you're going to compare them. They have to both be a 4, not a 1/4. So this would be 4 squared to the x, 4 to the negative 1. Rules of exponents. Power to a power. This is 4 to the 2x equals 4 to the negative 1. Hey, 4 and a 4. 4 to this 2x equals 4 to that negative 1. So this 2x has to equal that negative 1. Divide by 2. So x has to equal negative 1/2. Rewrite with a common base, which you might want to either print, download, print, something with the power charts that I gave you. 4. But it needs a calculator, so we'll go to there. On the calculator. And I told you we have 2 logarithm buttons that we can actually press. They tell you exactly and remind you exactly what they are. Right above the 2 log buttons, we have a 10 to the x, so this log, that is logarithm base 10. Down below is ln, above is e to the x, so that is a logarithm base e. So base 10. Log base 10 of x. This is the common log. No, it's a common logarithm. Base 10 is a common logarithm. When you have a common log, you won't always see the base 10. You won't see a 10. You'll just see log. So if you don't see a base and you see the LO and a G, all of it, that's common log. Just like when you have the square root of 36, you won't see a 2. But if you have a cube root of 27, without the 3, you're taking the square root. When you have a 3, it's a cube root. So there's a difference. When you have a square root, you don't put the 2. If you don't see a number here and it's log, it's a base 10. Okay? That's the common log. Log base e of x. So that natural base is written like this. Natural base, it's the natural log of x. I know they don't, but they don't write logarithm with a capital L. They write log. And they write ln. You know how many times that I've been teaching? Well, you don't need to guess. I've been teaching longer than you've been alive. Anyway, it's pronounced logarithm. I'll get students to go, it's pronounced logarithm. Why are you writing I? Where's the I coming from? I guess when they look at it in a textbook, when they write that lowercase l, it looks maybe like an I. But when I've been writing them down in class, I keep using the capital L's anyway. And when I type it up on the test, it's a capital L anyway. But when they do the problem, they put I's. What am I missing? Matters. So lnx, and there's an ln capital L right there anyway. So this is the natural logarithm. It's a base e. Base e. Those are the only two buttons you have on the basic calculator you're allowed to press, or you can press. Any other base, we have a translation formula that's a little bit later. If you want to make your life happy and happy and happier, these properties will make your life happier. These will be freedoms. They are, you know what we're doing? Not strong. Ready to go. They're the kind of question where you wouldn't even have to show work. Because if you know what that equals, you're good to go. So these are properties that are always true. So it's like knowing 2 times 2 is 4. So for any base, and I'm going to change the A's into B's. Log base B of 1 is always equal to 0. No matter what base, if you take a log base B, log base 10, log base 3, log base E, if you take a logarithm of a 1, the answer is always 0. Okay? It gives a reason. I just want to make sure you know the property. So that means over here with natural logs, the natural log of 1, because it's any base, so the base E is also going to be a 0. And here's why. Give me a number bigger than 1. 7. Log base 7 of 1 equals x. So we're solving for x. We translate. Base to the across equals what's inside. So what am I going to do?
The one in the base.
What's the what?
Flip to the one in the base.
No. Don't do it. You don't take what. What to the what equals what? No. Because when you say 7x, that's 7x. 7 to the x. Base to the across. So base, when you say 7x, that's what 7x means. And I'm getting that. It's not frustration. It's not anything, but that really does matter. It matters so much. Okay. Base to the, so 7 to the x equals what's inside? 1. Okay. How do I get a 1? What power will it have to be? The only way to get a 1 is if I have 7 to the 0. So x would have to be a 0. Okay, not you. So the only way I'm going to get a 1 is if I raise 7 to the 0. So any logarithm of a 1, I would have to raise the base to a 0. So the logarithm of a 1, no matter what base, is always 0. Log of 1, always 0. Log base B of 1, always 0. Natural log of 1, obviously, same rule, going to be 0. Log of 1 is 0. If one of your test questions will be, hey, what's the log of 1? And you're sitting there kind of going, that's the freebie. Second one. Log base B. Log base B of B. Well, how about this? Log base 5 of 5. I don't know what's called this. So base to the across equals what's inside. So 5 to the x equals 5. What's the power over here? What's the power if it's just a 5? That would be 5 to the what? 5 to the first. There's always 1. So 5 to the x equals 5 to the 1. So guess what? X has to equal to 1. Anytime I take a logarithm base b of itself, the answer is always 1. Log base b of b is a 1. Log base 12 of 12 is 1. Log base 19 of 19, 1. Log base square root 2 of square root 2 is 1. No matter what I take the logarithm base whatever of itself, it's a 1. The only way to get itself, you raise it to the first. If they're the same thing. The base of the logarithm is b. Inside is just a b. They undo each other, we get a 1. Natural log. So there's a base, there's an e down here. There's an e, log base e of e. There's an e in there. So it's natural log, so this is log base e of e. That's a 1. So when we write natural log of x, it's a base e. Number 3. Log base b of b to the x. And b to log base b of x. So logarithms and exponential functions are inverse functions. Inverse functions blank, and this is blank each other. What's that word? They undo each other. Inverse functions undo each other. So I have log base 3 of 3 to the 5th. And I want to know what that equals. I don't know, let's call it x. Anytime I don't know something, that's unknown. When we got something unknown, we call it log base 3 of 3 to the 5th. So then we translate. Base 3 to the across x. 3 to the x equals what's inside 3 to the 5th. Okay, I already have a common base. 3 to the x, 3 to the 5th. So what does x have to equal? So log base 3 of 3 to the 5th is just equal to 5. So do you kind of see what is going to happen no matter what? The base is a 3 of the logarithm. Inside the exponent is a base 3. If the bases are the same, log base 3 of an exponent base 3, they're going to undo each other. You're just going to get that 5. Because it's going to happen every time you convert it, no matter what. No matter what. Log base b of b to the x. The base is b. Inside is a base b. If the bases are the same, they undo each other. You just get the x. It's kind of messy right here. I'm going to rewrite this. This is a base b being raised to a logarithm that is base b of x. So it's an exponent, base b, raised to a power. That's logarithm base b. So the base of the exponent is b. The exponent is a logarithm base b. The bases are the same, so they're going to undo each other. Guess what the answer is? They're going to undo each other. You're just going to get the x. So if I gave you 23 to log base 23 of 5? What's the answer? 5. It should take that long. And yeah, you'll see something like that on the test. And it's another, hey, if I know my properties of logarithms, it'll do that quick. Otherwise, you're kind of just going, no. I thought there were going to be drinks here. So if it's an E, the natural log, so there's an E down here, of E to the X power is just going to be X, because there's already an E in this notation. And if you have E to the natural log of an X, so the exponent is base E, this logarithm is base E. So the bases are the same, they undo each other, you're just going to get an X. They undo each other. And then last but not least, the fourth property is if you're going to solve. If we have an equation and you're supposed to solve. If you have log base b of X equal to log base b of a Y. So they have to both be log base b's. They can't be two different bases. You can't have log base 5 on one side, log base 4 on the other. If they're both log base 5s or both log base 4s. If log base b of this equals log base b of that, then the X has to equal the Y. If they're both the same logarithm, the insides have to be equal. You don't care about the log base b anymore. You just let the insides equal each other. So I had log base 3 of X plus 2 minus 2 equal to log base 3 of 15. Since they're both log base 3s, then I just go X minus 2 equals 15, add 2, X has to equal 17. Now I could do the whole conversion thing, base to the across equal to left and side, but that might take you down a road where you're going to go, where do I go from here? Or if you know the property, if the bases are the same, you let the insides equal each other. And if it's natural logarithms, same thing applies. If the natural log of X equals the natural log of Y, then X equals Y. That's 4.2. 246. Number 2. The base of the blank logarithm function is 10. So what do we call what kind of a logarithm function is base 10? It's even on the board still. Common log. A common logarithmic function is base 10. And the base of the blank logarithmic function is base e. What kind of logarithm is base e? Natural log. I didn't write that up there, but it's a natural log. And then number 4, they use different, not base b or anything. Number 4 goes, if you have X equals e to the y, then what does y equal? So we're going to convert it into logarithm. Base to the across, because this will be the across. So how about you write it like this? So this is the across. How about we go e to the y equals x? If I have x equals e to the y, I can flip. So base to the across equals what's inside. So what's the base? E. E to the across equals what's inside. So what do you change this to when you have a base E? So y is equal to the natural log of x. And that's the big giveaway, is because it's a base E. Base E for a logarithm is natural log. Number 6. Fresh off the last thing we took in our notes. What is x? If you have the natural log of x equal to the natural log of 7, what does x equal? Quick. Natural log of this equals natural log of that, so this has to equal that. Well, you would have to translate it. E to this equals what's inside, and e to this is just 7. But we don't have to go there because we have this property. If they're both the same logarithms, base E, then you just let the insides equal each other. Okay. So that was just like a practice in terms of, can you remember to use the properties? I recognize that you get to use a property and then remember to use it. All right. Number 30 is the next in our difference. And number 30 says calculate a temp. And that's because down here at the bottom, that's what the directions are. Says use a calculator to evaluate the function as the indicated value of x, round up 3 decimal places. We have h of x equal 1.9 times log base 10 or common log of x. Now we want 4.3, plug it in 4.3. So h of 4.3 is going to be 1.9 times the common log of 4.3. So 1.9 times the common log. Here it is. Don't press second because you just want the common log. If you press second, then you're going to do 10 to the power up. We just want to take the common log. And then we punch in 4.3. It opened up a parenthesis, so I'm always going to close it. And you know what? Maybe they're putting IOG because they're looking right there and they see that's an I. But it's pronounced logarithm. And then you hit enter. And around the 3 decimal places, 1.204. And that's all you're doing on 30. 36. Solve for X. No calculator, you shouldn't need one. It is log base 4 of 4 to the third equals log base 4 of X. So you have on both sides of the equals log base 4 to log base 4. So if it's log base 4 of this equals log base 4 of that, then this has to equal that. You always simplify. So 4 to the third is 64. I know I'm going quickly, but you see how quick these problems are. Use the properties of logarithms to simplify this expression. Now, I didn't want you to use the properties of logarithms. Let's say I can't remember. Well, good thing you know how to, you have your mantra. So let's say you can't remember. Then I'll show you a property. Take you down property one. So 1/4 log base 4 of 16. So it's going to be 1/4 of something. So I'm going to focus on this log. I want to figure out what this is. Log base 4 of 16. I don't know, let's call it X. So base to the across. 4 to the X equals 16. What it's asking is this: 4 to what power is the 16? That's what a logarithm is trying to figure out. Log base 4 of 16 is asking 4 to what power is 16? 4 to what power? 4 to the X equals 16. So 4 to what power is 16? To the second. You would write both sides using the same base, common base. 4 to the X over here, 4 to the second. So that X has to be a 2. So this right here is just a 2. So this is just 1/4 times 2, which is 1/2. Okay. Now, this way where they say, use the properties. The properties are these over here. Because this is a base 4, maybe I can write the inside as a base 4. 16 is 4 to the second. This is log base 4 of 4 to the second power. And property number 3, log base b of x is just x. So this is 1/4 log base 4 of 4 to the second. That's just log base 4. That's a 2. And 1/4 of 2 is a half. I wouldn't mandate you do it anyway. I just want you to get the answer. What is 1/4 of log base 4 of 16? That's all. So now 68, we're converting natural log into exponential. The natural log cube root e equals 1/3. All you're supposed to do is write the exponential equation in logarithmic form. Well, in one direction. Write the logarithmic equation in exponential form. So change it into a exponent. What is the base of a logarithm, of a natural logarithm? Down here, what's the base down? There's an e. So the base of the natural logarithm is not this one. This is the one that's inside. There's an e down here that we don't write. So base e, what's the across? Base to the, what's across? Base to the across the equals, right? Base to the across, e to the 1/3. What's the inside equals what's inside? Rule number 9. Exponents. Anything to the 1/n. The denominator is the radical, the root you're going to take. This is the nth root of whatever the base is. I have e to the 1/3. So it's a cube root, and the base is e, cube root of e. $76. They want us to convert this into logarithms. So somebody took our natural log of something equals something and converted it into an exponent. We want to convert it back into a logarithm. Somebody took our natural log and did base to the across equals what's inside, and now we want to go backwards. Now, base to the across. The base is already taken care of because I'm using natural log. Okay, so the base is already here. Base to the across. So where do I put the 3/4? On the left or the right? On the right. Base e to the across. So the 3/4 is over here. Equals what's inside. So what's inside, I should have made more room. It's the natural log of the 2.1170 ... That's what it looked like before it was changed into an exponent. Let's convert it back. Mediate. Use the properties. Use the properties of natural logarithms to rewrite the expression. So for 88, we have the natural log of 1/e to the 4. Now remember, this is what's inside the logarithm. The base, when you have ln, there's an e in this base right here. if you don't remember the properties, let's just do it with our little chant. I don't know, let's call it. Convert base to the across equals what's inside. So if I convert the logarithm into an exponent, what's the base? E. E to the what?
X.
Base to the across. So E to the x equal what's inside? 1 over e to the 4th. Now, it's not going to work unless I have the base the same on both sides. On the left, it's e. On the right, it's 1 over. They're not the same. So I have to have e the same. So I have to flip this up. When I flip 1 over to the positive e up, what does it become? E to the? It becomes a negative 4 when I flip it up. If it's positive in the denominator, then I flip it up, it's negative in the numerator. So now this x is a negative 4. That's how you can do it with just that little chant. Base to the across equals what inside. Rewrite it. Or following the direction, right here, this is the natural log, and if you see it, inside is e to the negative 4. 1 over e to the 4th is e to the negative 4. And the property they're talking about is number 3. The natural log of e to the x. They undo each other, you just get the x. Because the base of the natural logarithm, there's an e. Inside is the undo each other, negative 4. Now, obviously, I'm not going to start at 4.3. We did a lot of examples, with all the examples in class. I do want to point out when it says and right there, I will be posting additional examples. There will be another playlist, and I will give you the direct link to it. But if you look right here, many years ago when I was still teaching from COVID, I recorded separate examples from 4.2, 4.3, and 4.4. Okay? So you will have access to these extra examples. And here it has 11, 17, 28, 32, 34, 80, 38, and so on. So I will post this. And I'll have one for 4.3 and 4.4 with extra examples for the homework, in addition to what we're doing in class. Okay? So it's not instead of coming to class, but it's stuff you can reference, come back to. So I will make sure you have access to this first one for 4.2. I will send the link to it today. Any questions? I won't send 4.3 or 4.4 yet. But you'll see this one. All right. So when you get that extra, that's what it's about. I had a lot more hair and I looked a little bit younger way back when.